The last section is linking all this together. Okay, we have a complete cycle here. A to B, B to C, C to D, D to E. Is thermal energy going to flow in or out? Well, we know that thermal energy flows in there, and it flows out there and there, because they go in the opposite direction. Where is the work done? The work done is when it basically is a change of volume. It does work there to the surroundings. Here, the surroundings do work to it. So B to C, it does work to the surroundings. D to A is the surroundings do work to it. Here we have thermal energy goes in there and there, a lot of thermal energy. And we have thermal energy coming out there and thermal energy coming out there. We have to calculate from a PV diagram the work done in a thermodynamic cycle. How do we calculate the work done? Here is the equation again. Remember, the work done is the pressure times the change in volume. Remember, you need to divide this. So, the two sections where there's work done, between B and C, is going to be P times delta V. It's going to be positive because the gas is expanding. So it's going to be P, this value for the pressure, times by the change in volume. So it's going to look like this. It's the area under this line. The pressure times by the change in volume. Okay. What about during the compression when it goes from D to A? This is going to be negative work, basically because the gas is being compressed. And it's going to be the area under this graph, between there and there. So overall, what happens with the work done? Well, it does a lot of work in this area, less work being compressed, negative, so this does a net amount of work to the surroundings. So there will be a lot of energy going in, more energy going in than comes out, but on the other hand, this system, this clockwise cycle, will do work to the surroundings. So heat will go in, a little bit of heat will come out, but overall it will do work to the surroundings. This is a heat engine. The heat does work. Now we have to solve problems involving the state changes of a gas. Changes of state, by the way, do not refer to changing of phase, i.e. from gas to liquid. Remember, we're talking about ideal gases. They do not change state or phase. How much work is done going from E to F? You can figure that one out. Pause. How much work is done by process B to A? Pause. How much work is done in process C to D? Pause. How much work is done from C to D? Pause. Now you can try to answer these questions. What has happened to the pressure, volume and temperature? Next exercise, calculate the work done by the gas here, question 20, and try 21. The answers are here. You can find the solution on Chris Hamper's webpage. Find the total work done in the process A, B, C, D, A. Pause. Find the work done here. Pause. find the net work done in this cycle. Pause. How much work is done here? Pause. How much work is done here? Pause. Now we have other questions for you to do. The answers are here, so you've got to work through the questions and see if you get the correct answers. Pause. Multiple choice question 1. Pause. Multiple choice question 2. Pause. Multiple choice question 3. Pause. Question 4. Pause. Question 5. Pause. 6. Pause. 7. Pause. 8. Pause. 9. Pause. 10. Pause. 11. We haven't covered that yet. I tell you what happens here. This is the equation. The thermal energy done is equal to the heat. No, the heat that passes in is equal to the heat that comes out plus the work done. For heat to go from there to there, you must actually do some work. So work goes in there, thermal energy goes there, and the two of them added together end up being here. 12. Pause. 13. Pause. 14. Pause.